Okay, recording is rolling. Welcome to Thursday, November 4th. So a few things today, but let's get a broad view of what's. I think I know how I want to finish the section over next couple weeks. So today and tomorrow we'll do as many of the college physics Texas problems as we can do. You guys remember AP Classroom Unit 5 has been open a while. Finish that by the end of this weekend so that Monday we can go over those. This will be the plan. Now, actually, next week's gonna be a kind of a weird, choppy week because Tuesday and Thursday are gonna be well, a little bit. Tuesday, there's some standardized tests that I have to proctor, so you guys gonna have a sub, possibly all period. I don't know. So I might have an effort sheet ready for you guys to go, and then maybe we'll just go over it the next day or something like that. But you guys are probably gonna get some time to at least work on the take-home quiz that I haven't given to you guys yet. I still need to write it, but I should get that to you guys by next week also. There's and then Thursday is next Thursday. 1 week from now is Veterans Day, so nobody's gonna be at school. But there is school Friday. Show up for your half-hour classes. So I do still want to do a Kahoot and a coefficient restitution lab. I'd like to get those in. I think those plan on those days, but we'll see when we get closer exactly how that's going to play out. Right, so today, top scientists. Right, here's how you guys did on the energy quiz. You guys did like super awesome because you guys know I give you really tough questions, but it's just for your name to be up here means you got a really high score, and a lot of you guys did. So yeah, I'm feeling really good about about this year. Yeah, have really great classes. Right, and then the other thing I want to mention is yesterday you guys did that collisions lab, and there's a detail that I want to mention about that. Draw a graph related to a case that you might possibly run into. So here's some example numbers from yesterday. You guys had collision lab. Now you guys tried a few trials where the two carts went like bam, collided together perfectly inelastically. That's the side. And then you guys tried somewhere they like boing, bounced off each other, and that was the other side where you had like two separate cart motions going on post collision. Okay. But I want to focus on the more straightforward one, simpler one, the inelastic collision, which AP usually asks about. Like if they ask about any kind of collision, like more often than not, it'll be an inelastic collision, just because the math is so much more straightforward. Like just boing, right, collide, and rip together. Right. And that's comparing your pre and post collision momentum numbers. Right? Ideally, these should have been the same, to verify conservation of momentum. I saw one of three different categories of outcomes. Right? So one category of outcomes is that these numbers actually were pretty close to each other, maybe like 22,000 versus 18,000 units of momentum, something like that. Okay, so that's awesome. Another category I saw is that these were just completely off, and so don't know exactly what led to that, but that would be something to think about. Like, why would these be just like randomly different from each other? What maybe procedures could have gone into that? Maybe there was some friction variable. This is probably the biggest factor that we ignored that would affect that outcome. But a third category I saw this yesterday throughout my classes, not all groups, but some groups, and I've seen this in the past, is that if your post-collision momentum was pretty close to half of your pre-collision momentum, right, then I have a pretty good idea of procedurally what happened to create that outcome. So, for example, if you had like 22,000 grams centimeter per second before the collision, and then you add momentum after, you get somewhere between like 10 to 12,000, which is like pretty close to half this number. I have a pretty good idea of what would have caused that. So I'll take you guys through this thought process, and you can follow this. And yeah, this is actually this might even be a good APFRQ. It's like why would that be? Something like that. Right? So there was one cart in motion before the collision, and then like bam, these two carts collide. Let me make a velocity in centimeters per second versus time in seconds graph. Let's say this refers to the post collision motion of the two carts coupled together, right? So bam, collide, they stick together perfectly inelastically. So this time zero right here refers to the collision point. So there's sometime before time zero where one cart was in motion, one cart was just waiting to be like slammed into, and then like bam, collision happens right here, right? And then we're looking at what happens afterwards. Right? Well, there was some post-collision velocity of the two carts coupled together. I'll call it v post, right, post-collision velocity. Now, if this were truly frictionless, which was the assumption, I mean, it's a low friction cart system, right? Low friction track. Right? If it were truly frictionless, then what would this graph look like? Shouldn't it just be just like that? Right? This thing can just like slide on forever. It can slide all the way around the Earth. If there's no friction, it can just kind of like it's an orbit around the Earth or something, right? Something like that. Right? But realistically, there actually was a little bit of friction. And if, let's say you gave it the original cart not a very strong push to start out with, okay? It's possible that after these coupled together, if they were going kind of slow, they may have even slowed all the way to a stop before the end of the track. Some guys may have had a situation. If you did, and then if you timed it so that you waited for it to come to a complete stop, you measured the stopping distance, then what would this graph look more like for that situation when you consider friction if it comes to a full stop? Wouldn't it actually look like this? Right? Because it would come to 0 centimeters per second at some point, right? After some tick, 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 times tick away. Right? So this is the no friction graph, right? And this is with friction. Okay? Now let's think about this graph, because V versus T graphs, this is one of the classic graphs that you guys have seen all the way back to August. See if you guys remember this. What does the slope of this graph represent? What physical property? Acceleration. Right? In this case, you might even say like deceleration, but we would say that negative acceleration, slowing down. Okay? And what property of this graph tells you how far this cart's rolled? Area under the curve. That's to say the area of this triangle. Right? This is like x post, right? The post collision distance that the two cars rolled before they rolled to stop with friction. Right. And if you did that, if you said, okay, here's how far they rolled, and then you timed that, how much time it took, and then you used that to calculate velocity, then you would not have been calculating the true post-collision velocity. You would have been calculating the post-collision like average velocity, right? And where is that on this graph? It's not this number. If you do this total distance divided by this total time, right? Let's say this area divided by this base. Hey, isn't that like average value? Did I tell you guys that that block of ice trick? Did I tell you guys that? Here, let's think about block of ice trick. Okay. Suppose I've got a couple of aquarium walls here. I have a big old triangle block of ice that represents how far the cars went. Big old triangle block of ice. Okay. And leave that there a few days and let it all melt. Okay. Isn't it going to melt down to about this level right here? Okay. And this would be the average, wouldn't it? Average velocity. If you have an average value of something, it's common to represent that with just a bar. Notice that's not an arrow. That's a bar. You guys see that bar? Okay. That means average. Okay. And in terms of the true post-collision velocity, what proportion of that is that? Yeah, it is half, isn't it? Right? Isn't this half of this? So this is the true post-collision velocity divided by 2. Right? Is it? And if you fed that value into your momentum calculations, that's why, or you would have ended up with half the momentum after compared to before. Right? Now, again, this isn't for everybody. This isn't for everybody's procedure. But if you timed it until you came to stop and you fed those numbers in, right, you would have ended up with half the momentum, and that is why. Okay. Guys, go back. Right, so let's switch over to college physics questions. Do as many as we can today and tomorrow, so that's a pretty good spot going for the weekend. Yeah. You want these? There. Yeah. All right, so let's see, the first sheet homework problem I had lined up was number 9. Got a 2.280 kilogram volleyball approaching a player horizontally with a speed of 15 meters per second. Okay. So it's nicely said horizontal, so you just simplify this into one axis, like an x-axis. The player strikes the ball with her fist and causes the ball to move in the opposite direction with a speed of 22 meters per second. Notice that they're using the word speed and not velocity. You guys see that? There might be a specific reason for that. Keep that in mind. What impulse is delivered to the ball by the player? Oh, impulse. Isn't that like a change in momentum? Right? So the ball had some momentum in one direction, then bam, it's hit back the other direction. That's a change in momentum. But there's a follow-up question. If the player's fist is in contact with the ball for this tiny fraction of a second, remember these collisions usually happen in tiny fractions of a second? Find the magnitude of the average force exerted on the player's fist. Hey, this sounds like that impulse formula that I gave you guys near the end of the notes the other day. So, number 9. We got, draw this out. What is a volleyball look like? I think something like this. Had mass, well, I'll just say M because that's the only mass we care about. Mass of the volleyball, 0.280 kilograms. I'll just use that book value because that's, I assume, the actual mass of the volleyball. But I'll change the speed value. So let's say V naught, right now your book said 15 meters per second, and make up something a little different. Let's say it's like, 12 meters per second. Okay. And then, bam! She strikes the ball and it's going to hit it back the other way. With a different speed. Now your book said 22 meters per second. I'll say the final, let's say like post-collision. Okay. So initial final is really like pre-collision, post-collision. Okay. Make up something else. Let's say like 24 meters per second. Something like that. Okay. Okay. And then one more thing. Now this is not for the first question, but the second question is that collision had some time interval associated with it, a tiny fraction of a second. Let's say it's like 0.050 seconds, okay, which is pretty close to the textbook value, a little bit different. Okay, so my values are pretty close to those, but a little different. All right, so first question, what is the impulse on the ball? Right, impulse, hey, that's change in momentum, isn't it? Okay. That's mass velocity post-collision minus mass velocity pre-collision. Isn't that change in momentum, impulse? Okay. So impulse, when you see that word impulse, think change in momentum. Right? Okay, so I could factor out the mass of the ball and just do change of velocity. Right? Mass times change of velocity. V post minus V pre-collision. Okay, now here's where you could possibly get tripped up. There's a difference between the word speed and velocity. Right? Now look at, well, we know what mass of the ball is. It's 0.280 kilograms. Okay, so that's all fine and good. Okay. Now here's where, I bet most of you guys get this right, but some of you guys might be tripped up by this. Look at my velocity values, or my speed values, I should say. Like 12 meters per second and 24 meters per second. What is the difference between 12 to the right and 24 to the left? What's the difference? 36. 36. Right? Let me draw this on a number line. Okay. I like the number line model for this one. Okay. So this is like 0 meters per second, and we're going let's do 12 to the right. Maybe I'll call it right the negative direction. So negative 12. Right? And then positive 24 because it changed direction. Right? If you didn't see it before, do you guys see it now? That the difference between 12 in one direction and 24 in the other direction is actually 36 units. In this case, 36 meters per second. It's 24 minus negative 12, right? Okay, see that? 24 minus negative 12. Right. So I'm calling left the positive direction. Right. So if right is the negative direction, then as a velocity, I should really call this number negative 12, shouldn't I? Right? Like negative 12 meters per second. Right. So I've got 24 meters per second minus negative 12 meters per second. That is 36 meters per second is the change in velocity. If you multiply that by the mass of the ball, you get its impulse, change in momentum. Okay. I'm looking at 10.08, and that would be, okay, I could say kilogram meter per second. Kilogram meter per second, right? I could also call that 10.08 Do you guys remember what the alternate unit for impulse or momentum is? Could be kilogram meter per second, but it's also equivalent to what mix of metric units? That includes newtons. Newtons times what? Seconds, Newton seconds, right? That's the same thing, right? And if you got an AP question, like multiple choice question, they could very well throw either of those units at you, and then be ready to fill either one of those, right? Okay. And actually, the second way I wrote it, Newton seconds, is a better way to think of the setup for the follow-up question, because they told you a time interval, in seconds, and said, what's the force? Oh, hey, look at that. You guys see how this is exactly going to feed into the framing of the next question? Right? If they told you time interval, boom, seconds. They're asking for force, boom, newtons. You guys see that? Okay. So let's go to that impulse formula. Oh, yeah. Yeah. Okay. So impulse, delta P. I've been trying to do these arrows, right? Need to get in the habit of doing that for vector values. I think it's all the vectors, right? You could say it's mass times change of velocity, and we just calculated that. You could also call that force times time interval. Remember that straight from the notes, right? Impulse formula. Right. I really need to turn this into a poster, make a whole graph out of this and the whole deal. Okay. So, guys, what kind of force is this? Is this average force or maximum force? This is average force. Right? I'll make a graph after we actually answer this question and the whole deal. Right? So the 0.280 kilograms times the 36 meters per second change in velocity. We calculated that already. You guys remember that came out to 10.08. 10.08. Right? Either kilogram meter per second or Newton seconds. I'm going to use the Newton second version just so that it very clearly lines up with the questions being asked here, right? Which is, what is the average force for solved for? Right? And they told you the time that collision acted for. Very tiny fraction of a second. Maybe like this many seconds, for example, right? How many seconds? Okay. Okay, so if you divide both sides by that number of seconds, you guys see the seconds just kind of cancel out. You'll end up, some number of newtons to represent a force. Right? So what is 10.08 Newton seconds, all divided by 0.05 seconds? I'm looking at an average force of 201.6 newtons. Okay. Now that's too many sig figs, so maybe I could say like 202 or something like that. I don't really know the 0.6. We don't really have 4 digits of precision, I should say. Okay. But maybe like 200 and some newtons. Right? About a 200 Newton force to make that happen. Right? Right. Guys good? Guys good? All right. That is, that's all they asked for. We could move on, but I don't want to move on. I want to make a graph. You could actually answer this graphically without the equations at all. Well, maybe you need a formula for area of a triangle or something. What would that be? Right. Force in newtons as a function of time and seconds. Right. So that time interval lasted tiny fraction of a second. So maybe like from here to here. That's the whole collision. Okay. Now, what does this graph actually look like? Okay. That was not really addressed by the problem. I guess could sort of textbook, very rough textbook value be a constant force, but realistically, how these graphs turn out is they tend to take these triangle shapes. Okay. And I showed you guys with the bat and the ball yesterday. So here's the volleyball, just about to strike her hands. Okay. Then here's at this point the volleyball is being maximally smashed, right? And then at this point right here, here's the volleyball like leaving her hand. Right? So it's just making contact, it's getting super pushed, and now it's changing direction, and now it's leaving her hand right here. Okay, you see it? Okay. Now, where does this number, this 201.6 newtons, fit on this graph? Is it this peak value? No. Is it halfway up? Yep, that's it. Okay. This is F average of maybe I'll round it to like 202 newtons. Right? That's to say if you had, this is a block of ice, right? This shape right here. Oh, this triangle, what physical property does this area represent again? Not the force, the impulse. Yeah, impulse. Right, delta P, change of moment. Right. Anytime you see a force versus time graph, be ready to field an impulse momentum question. Okay. Right. So here's the average force that we calculated. Yeah, if that was a block of ice and you let it melt, wouldn't it melt down to like that level and that you'd have this rectangle? Average force times time interval. That's the impulse also, isn't it? Okay. So if so why am I bringing all this up? What if this volleyball was made out of some material? You say, oh, you can only put such and such maximum force before like the seams break and it busts the volleyball. Right? Maybe you actually wouldn't be interested in the average force. You'd be more interested in like this maximum force. Miss this line a little bit. F max. Right? And just by glancing at the graph, you guys can very quickly see what F max is. Right? What is F max? You guys see it's going to be 404 newtons, which is double the average force. Guess it? Yeah. You guys got on number 9. Next one, number 25. These are the numbers are a little bit out of order. I'm sure there's some reason I was doing this. 25. Oh, hey, we got a graph. And it's a force versus time graph. Yeah, remember, whenever you see force versus time, it's going to be a momentum impulse question. Let's see what the exact question is. The force shown in this force versus time diagram acts on a 1.5 kilogram object, so mass object. Find the impulse of the force, the final velocity of the object. Oh, okay. I guess there was another question, but I just cut it off. That's all I cared about there. Okay, so let's find the impulse and the final velocity. Okay. So I'm going to make up my own graph. This is for, what's it? Say 25? I think it says 25, right?
Yeah.
Yeah, thanks. Yeah. Someday I think one right. Okay. So they gave us this trapezoid looking shape. I'll make a trapezoid too. I'm just going to change all the numbers. Okay. So, you got time, tick, tick, tick in seconds. Let's call this like 0.1, 0.2, 0.3, 0.4. Oh, I'm doing so silly. Can't believe we did that. Wow. So 0. Of course it starts at 0. Never make that mistake. 0, 0.1, 0.2, 0.3, and 0.4 seconds. Okay? Oh, sorry guys, gotta zoom out. As you can see. All right, and then force in newtons. Let's have this thing go up to maybe like 10 newtons. So 0 newtons, 5 newtons, 10 newtons. Okay? So, question, what is the impulse? Isn't the impulse the area of this trapezoid? Right? Delta P, impulse. Right? And that trapezoid, couldn't you just split that into a rectangle plus a triangle? You see that? Okay. So let's do that. So delta P is the rectangle plus triangle, okay, on a force versus time graph, okay, which would have momentum units. That rectangle base times height, that is 0.2 seconds times 10 newtons. Okay. Plus the triangle is, well, that's 1/2 base height, so 1/2 times, right? Now, this has a base of 0.2 seconds. I know in your paper, it's a little bit different shape, but I'm going the base of this triangle, right? So 0.4 minus 0.2 is 0.2. Right? And then the height of this triangle is 10 newtons. Okay. So that looks like 2 Newton seconds plus 1 Newton second is going to give you 3 Newton seconds, or 3 kilogram meter per second. Right? Since it's impulse, more commonly they use the unit Newton seconds for impulse. Okay? So force times time interval. Guys good? Yeah. Right. And then they did tell you the mass of the object and asked what's the final velocity. Right? Do you guys see why it would be important to know the mass to be able to answer the question, what's the final velocity? Because if something's very, very heavy, it's going to give you moving very fast or very slow responding to this impulse. Yeah, very slow, right? Like if you put this impulse on a bowling ball, maybe it budges a little bit. If you put this impulse on a golf ball, ping, take off. So let's get a mass of the ball. Now this would have to be given. I'm gonna say, see, what's a bowling ball about? Bowling ball is probably about 5 kilograms. Let's say we put this impulse on a bowling ball. I want to know what's the final velocity of this bowling ball. So we got mass times change in velocity is equal to force times time interval. Is equal to the impulse. And you know what force times time interval is, impulse, because we just did that right here. Pop that in. So 3 Newton seconds, that's also kilogram meter per second, is equal to a 5 kilogram bowling ball changing its velocity by how much? Say it started from rest, what would its final speed be? So 3 divided by 5, isn't the change of velocity going to be 0.6 meters per second? Kilogram meter per second divided by kilograms, just meters per second. Now that's the change of velocity. So to get the final velocity, you would have to know the initial velocity and just add it to that. If it started at rest, then this number plus 0 is just that number, right? So here, final velocity is equal to initial velocity plus the change of velocity. And if initial velocity is just 0, then the final velocity is also 0.6 meters per second. Guys good? Ooh, this next question I like a lot. Number 18. We're going to sort of take this into 2 dimensions. It's like if you've been paying real close attention, every single momentum problem you guys have seen so far has been in 1 dimension. Okay? So here's a first sort of 2-dimensional type problem. What if you have this ball of this given mass, so many kilograms, that goes boing, bounces off this wall? Okay. They told you, see, the speed, so many meters per second, and this angle, so many degrees. It bounces off the wall with the same speed and angle that it was coming in. So whatever speed it's coming in with, it boing, bounces off at the same speed. Hey, do you think that if it bounces off with the exact same speed, that might represent one of the boundary conditions of possible collisions? In fact, that collision, based on that fact, must be perfectly what? Must be perfectly elastic, because kinetic energy is conserved, isn't it? Your 1/2 mv squared going in, and your 1/2 mv squared going out have to be the same value. That would be perfectly elastic, wouldn't it? Okay, so that's nice to know. If the ball is in contact with the wall for this tiny, tiny time interval, fraction of a second, what average force was on the ball by the wall? What average force? Okay. So the fact this is in 2 dimensions and momentum is a vector quantity. What I'm thinking is, well, let's split up our thinking. What's going on this y-axis versus what's going on this x-axis, right? So it's number 18. Back up here. All right. So here's our axes. We've got x-axis, y-axis. This ball is coming in at a 60-degree angle to the wall. So this angle is 60 degrees. I'll keep the same as both angle. Right? But you guys know 30 and 60-degree angles are those are pretty special angles, sine and cosine values. Right? And it bounces off, but boing, rebounds with the exact same speed. So to give you guys some values, let's say the mass of the ball, I'll call it 5 kilograms, like that bowling ball from before. Right? And I'll have a speed of, I'll say v is equal to, let's go 20 meters per second, like that. Boing, okay. And this speed is also 20 meters per second. Okay. And it would be a velocity if you also specify this angle. Okay. Guys, good so far? All right, so I bet you guys are knowing what the next step is going to be, which is we're going to break these into components, right? Vector components. So the ball going at some weird angle. Well, that's kind of towards the wall and kind of along the wall. So I'm going to get some dash components here. So there's v sub x and v sub y. And then we got v post collision. It's sub x and sub y components. Okay. Hey, did you guys see a couple of right triangles? For instance, like vector components. A couple of right triangles. Okay. They call it congruent triangles if they're like exactly the same size. So, do you guys know how to get these components? This would be 20 meters per second multiplied by what? V sub x is 20 meters per second multiplied by. What do you do with a 60-degree angle? Sine or cosine? Sine. Yeah, sine. Sine 60 degrees because it's opposite of that, right? Okay, so this one must be v sub y is, you can think of these like vector component vectors, right? 20 meters per second times cosine of that 60 degrees. Right? Hopefully, this is true in general, but with this one also, see if you guys can stay a step or two ahead of me, because if you can have an idea of like where we're going with this question and you can figure out each step, then that's a good sign that you know what's going on. I'll have this Vy post. I guess this is like pre, this is post, and V sub x post. But they would be the same values, wouldn't they? So 20 meters per second times cosine of 60 degrees again, okay, and 20 meters per second times sine of 60 degrees. Okay. Now that's just based on the geometry, treating those as just triangles. But one more little detail here, right, is that we'll think about the directions of these things. Let me start with the one that's a bit more straightforward, which is just the y direction. Right? Did the ball change what it was doing at all in the y direction? No. So do you think an impulse question, an impulse would be like change in momentum, has anything to do with the y direction? It does not. Right? All the direction change has to do with like the x direction, isn't it? The x-axis. So yeah, we could get a number for this, like 20 cosine 60 degrees. Okay. Oh, that's exactly 10 meters per second. I should have known that without the calculator, because cosine 60 degrees is exactly half, just like sine of 30 degrees is. You're playing off this 30-degree angle. But so that doesn't change. That's just the same. No change there. Okay. But what about the extra? Hey, if it's going, here, let's get a number for this. Sine, okay, this is 17.3 meters per second toward the wall. Okay. This is the same magnitude leaving the wall, 17.3 meters per second, right? Except that the fact that it boing, rebounded the other way, what one more detail do I have to consider? Negative. Yeah, I have to assign a positive, negative direction. Let's say right is positive, left is negative, so that would mean that this is negative, right? Is that true? Right. You guys right? Right, so if you want to figure out, yeah, let's well, they said what's the average force, right? So let's go to impulse equation. So average force, notice I said average force, not maximum force, right? Talked about that earlier. Right? Times time interval will result in a mass times change in velocity. There's your impulse. So impulse. Okay. And hopefully we have three of these four things so we can solve for the average force. It's going to be kind of a tight squeeze to get another paper out. Because we're ignoring all the y direction stuff anyway, right? There's no change there. So all I care about, I can just cover that up, whatever. All right, so average force times time interval. They did give you a tiny time interval. I'll call it 0.05 seconds, like the previous example. Your book gave you a different number. Okay. Okay. You have to know you do have to know the mass of the ball. Right? I was saying 5 kilograms. So I'll do 5.0 kg. Okay. And then change in velocity. Okay, well, here's the trickiest part of this, but I bet maybe all of you guys see this, what it's going to be. Okay. Guys, we got 17 meters per second toward the ball, 17 meters per second away from the ball. Okay. What's the difference between negative 17 and positive 17? negative 34. It would be. Let's do final minus initial. Okay. So negative 17.3 meters per second minus positive 17.3 meters per second. So if you put this on a number line, the difference between negative and positive 17 is 34 units, isn't it? Okay. In this case, it's negative, final minus initial. So F average looks like it's going to be 5.0 kilograms times negative 34.6 meters per second, include another decimal place, all in 0.05 seconds. Okay, okay. Just rearrange that. Okay. Pause for a moment. Does this look like Newton's second law of motion? F equals ma, right? Delta v over delta t. That's acceleration, isn't it? And impulse formula is a stone's throw away from Newton's second law of motion. And so 5 times negative 34.6, I'll divide by 0.05. I'm looking at an average force, oh boy, 3460 newtons. Okay. But that could make sense because I have a bowling ball, like 5 kilograms, that's about a bowling ball. And that's a really fast motion, right? 20 meters per second, that's, I want to say like 40, 50 miles an hour, something like that. So, yeah, that looks about right. You do a huge force to bowling, like reverse the motion of that bowling ball. Now, one of the things you get from this class too is to think in terms of like relationships and among variables, right? So what if you did this? What if the time interval for the bowling ball to go boing off the wall? What if you increase that time interval? Let's say instead of just a solid wall, like a concrete wall, it's like bam, like that. What if you put like a trampoline type material, so it went boing, like that, boing, but you got all the same numbers otherwise. So the mass of the bowling ball, obviously the same. Let's say the change of velocity was also the same. Like that all worked out the same. These triangles are the same. Okay. But the time interval is now increased. So instead of like bam, now it's boing. So you increase that time interval. What happens to the resulting force to make all this happen? Increase or decrease? If you increase the denominator of this fraction, the force must decrease. That's an inverse relationship, isn't it? I bet if you were, say, like jumping off the third story of a building, let's say the building's on fire, you got to jump out. Okay. Would you rather crash against a hard sidewalk or a trampoline? But boing, what sounds better? I want to hit that trampoline because your impulse is going to be the same, but that force would actually go down, wouldn't it? All right. Number, let's say 19 up here, I think. The front. So many meters of this kilogram car is designed as a crumple zone that collapses to absorb the shock of a collision. Right? Okay, so now we're getting like car safety and car design. Right? So I mean, just statistically, there's going to be some number of car crashes. Right? So it's like I want to say that 40,000 car crashes in the United States per year, something like that. So yeah, so if you're an engineer, you got to design a car with that idea in mind, right? Some of these are going to crash, right? Just statistically. If a car traveling at this speed stops uniformly in that distance, let's see, how long does the collision last? Probably a tiny fraction of a second, right? What is the magnitude of the average force on the car? Ooh, probably pretty similar to what we've just been doing. And what is the acceleration of the car? Ooh, that takes us back to maybe like kinematic motion way back in the day, right? You guys remember like G-force, right? Like if the acceleration of the car was negative 10 meters per second squared, you'd have about 1 G worth of horizontal acceleration. Right? Actually, that's exactly what it's saying to do in this last bullet right here. Express the acceleration as a multiple of Earth gravity, right? Okay, let's do it. And of course, I also want to talk about what if you change that crumple zone, right? What if you made it like more or less? How would that affect things? Okay, so say you got a car. Maybe it looks like this. Right. Drawing you guys a fancier looking car. Because cars drive in some initial velocity. Give you some numbers here. So I'll have this going at, let's say 30 meters per second. Right. Say the mass of the car is, I'm going to make it 1,900 kilograms. Okay. And when this car, say there's a wall here and it like smashes into this wall, and the wall's not moving. That might now look like this. Here's your after photo, before and after. So, looks like there was some crumple zone. Maybe I could call that like a like delta X, something like that. Like a change in, right? So this whole front of the car just crumpled. Okay? Compare this to where it was up here, like this. Okay? That's the part that's about to get crumpled, and then there it is crumpled, like before, after. Okay? Before collision, after collision. Okay? Oh, and they did give you a value for that. So let's call that like maybe 1.5 meters, or something like that, right? Hey, have you guys ever seen? Ooh, I bet I can dig this up on my computer real fast. It's related to this question. Sends motion. Here it is. Here it is. Flip my screen over. I flip my screen for this video. You guys can all see this. Present screen 2, share. All right. When you guys are driving along the interstate, sometimes you'll see some of these out there. Right? That's called an attenuator. What's that for? Well, that's pretty much exactly what we're solving here. You guys see this big old concrete barrier right here? Right? Suppose that maybe, I don't know, you're driving, maybe you're sleepy, maybe you're distracted, who knows, stuff happens, right? And you slam into this concrete barrier. Well, would you rather that happen or slam into this thing that's gonna like crunch? Probably hit this thing instead, right? Because then the rate that you slow down is going to be like slower. The G-force is going to be less. But the right, and then that impulse. Now the impulse doesn't change. The mass time change of velocity of the car, but the average force would, right? Because if it's extended over a longer distance and over a longer time, right? So that's what that's all about. So let's go back over here. Right. And in fact, if you hit that thing, it looks like your crumple zone will actually be several meters instead of maybe just something to do with the car itself. But okay. And so back to here. Is that what they gave us? Okay. What's the average force on the car? Is the first question. No. How long does the collision last? Right? Which is actually a better question because they gave us distances and B final 0, of course. Right? They gave us speeds and distances. Right? So how are you going to get the time interval for all this to happen? The time. Do you think you'll have to probably use these guys right here, right? So let's see, we're going to rest from some speed. You're looking for time, based on distance. Which one do you think it's going to be? I think we're going to have to use some of these in combination with each other, right? Because we could use this one to figure out acceleration, and we can take that acceleration, plug it into one of these top two to figure out the time. Okay. Let's do that. We got to figure out the acceleration. Okay, so actually, I start answering question C first. We're going to question C first. Okay, so let's do final velocity squared is equal to initial velocity squared plus 2ax because they told you the crumple distance, right? Going to 0 meters per second. Square that, right? From, I told you guys 30 meters per second. Your book value is a little bit different. Plus 2 times the rate it's slowing down times, now the stopping distance was, I'm saying this many meters, so it's a little bit different. Right? You guys can do some algebra, right? 30 squared, that's 900. Subtract that over, divide by 2 by 1.5. Right? So a few algebra steps later, I'm getting the acceleration is negative 300 meters per second squared with my numbers. Now your book numbers are going to, of course, a little bit different. That should be kind of close to that. Hey, if there's, or I should ask you guys, how many G's is that? How many G's? 30. You guys see 30? Because take the magnitude, 300. And you guys know every 10 meters per second squared represents 1 Earth gravity. That is 30 G's, isn't it? Right? You'd feel like 30 times your weight, but only for a tiny fraction of a second. Okay? You guys remember seeing that guy in the centrifuge? He went up to like about 10 G's. You guys know that? Like 9 or 10 G's? Or I think so. All right, so that was question C. Question A, how long does the collision last? Okay. Well, now that we know the acceleration, you can go back to another kinematic formula. So final velocity is equal to initial velocity plus AT. Solve for that. So going to 0 from 30 meters per second. Okay. And you know acceleration is now negative 300 meters per second squared for some time. Oh, these numbers work out really nice. You guys see it's just going to be subtract that, divide by that, a tenth of a second. Right? Guys see that? Okay. So that's question B. Or no, A, I should say A. That's question A. Okay. Finally, question B. What is the average force on the car? Average force on the car. Right, so probably we have two ways of getting this now. You could do force times time interval is equal to mass times change of velocity. Could do that, right? Or you could do F equals ma. Let me try both ways. So ma, the mass of the car was 1900 kg. The acceleration was 300 meters per second squared, negative. So what's 1900 times 300? Right. I'm looking at 570,000 newtons. If I do it this other way, solve for this force. Okay, so the mass of the car is 1900 kilograms, times change of velocity of the car was 30 meters per second. That all happened in a time interval of 0.1 seconds. Again, exactly the same thing, 570,000 newtons. Right, if you plug in the numbers for you get the exact same thing. All right, it's a good pause point. We'll do more of those tomorrow, and that'll take us to the next weekend. You guys have a good Thursday.